morning. I wonder whether we should wait for more audience or whether we should just start. Or maybe we just start, otherwise we're going to end too late. Okay, so let's go on. So last time we've seen that for, we looked at organic operators. And we saw one of the basic theorems, which was that due to Pasteur, for H omega organic, there exists sigma closed such that the spectrum of H omega is equal to sigma omega almost surely. Right? Now, there is another result of the same type, which is a bit more precise, right? So, spectral components. So what are the spectral components? You remember if you take A, be self-adjoint on some Hilbert space that I assume always to be separable H, then we can do the following thing. We can define the spectral measure of A. So what is a spectral measure? It's just a projection valued measure. So let's say it's a family EA of H that goes from the Borelian sets of the real line into orthogonal projectors on H, right? Such that, well, you have the following things roughly. EA of the empty set is equal to 0. It's the zeroth projector. EA of the whole real line is equal to identity. Second, if what? If you take, what should I call it? Omega, not omega, maybe, Borelians, let's say B1, countably many Borelians, such that they are disjoint 2 by 2, then of course the union of this is a Borelian set, and one has that this projector is actually the sum 1 E, right? We have this, where here we are summing projectors, so we need to understand what is the convergence of this, right? This is in the strong, so convergence is strong. Meaning that every time you add a vector, you take this applied to some vector, right? So here you have a sum of vectors, and this sum converges in norm. It's not the norm convergence, right? It's not that this is not norm summable because all of these have norm 1, right? So this is just strong convergence. And in particular, the other thing that you will have, which is that if B1 and B2 are Borelians such that they do not intersect, then EA of B1 intersected B2 is just, in general, if you have two Borelians, they intersect or not, B2, right? And you have this essentially is a consequence of this modulo something which is the commutation of these. Let me think now. One thing maybe I can ask either for this, or I ask that EB1 EB2 is equal to EB2 EB1, right? They commute. It's the same property. If you have this property and either one of those, these two are equivalents once you know this. right? And so this is what is called the spectral measure. And once you have this spectral measure, what happens is that you do the following thing. Then you have, there exists spectral measures for a given self-adjoint operator. There exists a spectral measure such that if you think if you can write A, we can write A as the integral over sigma over the spectrum of A of lambda dEA lambda, right? So I need to give a meaning to this thing. What does this mean? It just means the following thing. For any phi, you can do it for a single vector, then you can just polarize the identity. For any phi psi, let's say phi psi in H squared, you have that A phi psi is equal to integral over sigma of A of lambda dEA lambda phi psi, where this is a complex measure, right? Sorry, not phi psi in H, such that phi is in the domain of A, right? And psi belongs to H, right? So you have this, and maybe I should have said before the following thing, is that phi belongs to the domain of A is the same thing as asking that the integral of lambda squared dEA lambda phi scalar phi is finite. Right? So, I guess you're familiar with this, right? That's just to recall, because some people asked me at the end of the last lecture some stuff about self-adjoint unbound operators, so they seem not to be familiar, but if you're all familiar, that's fine. Okay, and then, of course, there's one standard thing, is that you can, once you have this DEA, you can do the Lebesgue decomposition. Lebesgue decomposition, that is just, so you have this measure, right? DEA, and you can write it as DEA AC plus DEA singular continuous plus DEA pure point. So what does this mean? Well, you know that if you have a real valued measure for a real or complex valued for, yeah. So I write it this way because this is something a bit different, but for real valued measure mu, you have the Lebesgue decomposition. D mu can be written as d mu AC plus d mu pure point, singular continuous, plus d mu pure point, right? That's just the Dirac masses inside the measure. That's the absolutely continuous, so this can be written as some function f times d lambda, Lebesgue. That's Dirac. And this is what remains, right? That's what left over. It's called singular continuous. Masses. And so for the operator, what you do is the following thing. You look at, well, for I don't know, epsilon belonging to SC, PP, and AC, you look at the following thing. You look at the phis such that d EA phi scalar phi is actually equal. So this is a real valued measure, right? Because these are orthogonal projectors, so this is real valued, actually it's positive. And you look at the phi such that this is, for example, equal to, so if you call this mu, is equal to mu epsilon, right? So it has only one component. Okay, you look at the vectors phi such that it has only one component. Right? And you call this H epsilon. This gives you a subspace, right? This gives you a subspace of the total Hilbert space. And what you can show is that HAC direct sum HPP direct sum, orthogonal direct sum H AC is equal to H. Right? These three subspaces are orthogonal to each other, and their sum is total subspace of H. And then this is just DEA epsilon is just DEA, and the other thing is that H epsilon A, right, intersected with the domain of A. This is inside or inside H epsilon. So these spaces are stable, right, under A. So you can restrict the operator to the space. H epsilon. You can restrict H epsilon to the space, and you define the measure just to be the spectral measure of the restricted operator, right? And so inside this writing, you see that there are two things. There is first this kind of decomposition, but there is also this orthogonal decomposition, right? It mixes up the two things. Okay, so if you take a general vector, phi, which is not in any of these components, which is the direct sum, which is the sum of three of the components, you apply this to this, you see that you have various parts of it, right? So, well, I guess this is nothing new to you, for most of you at least. Okay, and now the theorem is the following. So, theorem. This is due to Pasteur also, and at the roughly same point of time, there's Kunz and Suyar. And it says the following thing. I won't prove it, but it says that, well, let H omega be ergodic. Then, for epsilon belonging to pure point, singular, continuous, and AC, there exists some closed set sigma epsilon, closed subsets of the reals, closed, such that what? Such that omega almost surely sigma epsilon is equal to the epsilon component of the spectrum of H omega. So the spectral components, pure point, singular, continuous, and AC, are almost surely the same for our operator. Right. A remark about this is the following, is that sigma pure point of H omega is not the set of eigenvalues, it is the closure of this set. Right? That's the closure of the set of eigenvalues. Right? It's not like in the discrete case. Well, of course, in the discrete case, as you have discrete points, the eigenvalues are discrete. If you take the closure or take the set itself, it's the same thing, right? No difference. But here, typically, it won't be the same thing, because what's going to happen is that the eigenvalues will be dense in some subsets, right? When you take the closure, you get the whole interval. For example, if they're dense in an interval, right, or union in intervals. So this makes a big difference. Well, the situation is as nice as one can hope for, right? What can I say? What else can I say? This is as in the previous lecture. This justifies that one speaks of a single ergodic operator instead of a family of operators, right? But one thing one should keep in mind is that these eigenvalues, usually, or at least in all the models I showed and in many other models, not always, but in many other models, they vary, they fluctuate. The eigenvalues themselves vary very much with omega. If you change omega for another one, even in this almost sure, in this probability one set, right, you're going to change the spectrum, the eigenvalues, the actual value of the eigenvalues. But you're not going to change the closure of this set. Okay, eigenvalues actually move very fast with omega. Okay, they depend very much on omega, but their closure doesn't. And we're going to see this through a number of things. We come to this at the end of this lecture, but to see this. Okay, now, one of the things I may want to do is to compute, right? The spectrum, the almost sure spectrum, it's a C component, it's a C component, it's pure point component, right? And of course, this is, in general, it's a difficult problem. I mean, it can only be because if I give you an n by n matrix, compute its spectrum is not an easy task, right? 2 by 2 is fine, 3 by 3 is already more difficult. Larger than that is, essentially next to impossible by hand, right? I'm exaggerating, of course, but there is, in this case, a simplification essentially due to these theorems. The fact that the spectrum, as a set, is very much invariant under the move of omega, right, is a big help. So you have an object which depends on many parameters, but actually it doesn't depend on the parameters. So you have a lot of freedom to move the parameters around, which gives you a good freedom to analyze what this object is, right? So, but nevertheless, to compute these is very model dependent. So I'm just going to write down one result to give you an idea what it is for a single model, which is the Anderson model, right? Actually, that it's really Anderson is not important in the sense that the kinetic energy is not so important, but so we have the following theorem. So remember, the Anderson model is on ZD, on L2 of ZD. Oops, ZD. You consider H omega equals minus Laplacian plus V omega, where V omega is just of U at n is just omega n U times n, and omega n are IID random variables. Right? The fact that here you have the discrete Laplacian is not so important. If, for example, you replace the discrete Laplacian by a Fourier multiplier, right? Meaning that, so this has the symbol, if you think of it as a Fourier multiplier, it has a symbol which is the sum of the cosines, twice the sum of the cosines, right? In the way I normalized it in the last lecture. If you take another Fourier multiplier, the result I'm going to give you is the same, doesn't change, right? And so the theorem is the following. Omega almost surely, the spectrum of H omega is equal to minus 2D plus what? Plus the support of the random variable. Let's say omega 0 there, IID. Support of omega 0. What is the support of omega 0? All right? Well, it's the essential, if you want, yeah. What I write, support omega 0, which is not very tidy, is the essential support of the probability measure of the probability distribution of omega 0. Right? This is what I mean with support. Right? You have this random variable. Okay, you look at this distribution function, right, which is a measure on the real line. And support of the random variable is what I mean is the support of the probability distribution. Okay. Okay, and here this comes, of course, from my normalization of the Laplacian. Right here, recall the Laplacian minus Laplacian of u at the point n is the sum over the nearest neighbors of u of n. Right? If you normalize Laplacian differently, of course, this changes. You just have to change this set. So here, if you want another way to write it, is the following: is that this is just the spectrum of minus Laplacian. And this is just, here you have another ergodic operator. Sorry, if I look at V omega. Here I look at V omega. Let me write it in this way. Sigma V omega, where sigma V omega is the almost sure spectrum of V omega. This is also, the potential alone is also an ergodic operator, right? You can check it. You can check that it satisfies exactly the same assumptions as the Laplacian plus the potential, right? Because the shifts here, these are IID random variables. The shifts are ergodic, right? And the shifts are, so you get that this is an ergodic operator. So it has no almost sure spectrum. So actually this theorem can be read as the spectrum of this operator is actually just the spectrum of this one plus the spectrum of that one, which is in a way miraculous, right? I mean, usually if you take the sum of two matrices, you're pretty lucky if the spectrum of the sum is equal to the sum of the spectra, right? This is not something that only happens if the matrices in general, if the matrices commute, right? This is the condition, right? This is the usual condition that you can give where you generally have, if A and B commute, A plus B has spectrum of A plus spectrum of B, right? Here, they don't commute, no question. In general, they don't commute. I mean, this is a Fourier multiplier on the Fourier side, and this is a multiplier on the position side, right? And so these two things do not commute. Right? Nevertheless, you have this, but this is because of the randomness. Right? That's one of the effects of the randomness. Let's prove this. It's actually quite simple. It's actually quite simple. So what do we need to do? Well, we're going to prove the double inclusion. The first thing that is easy is that this direction, or this inclusion, is clear because you always have, right? One always have that sigma of H omega is contained in sigma of the Laplacian plus sigma of V omega, right? This inclusion is clear. You just take, here we're dealing with bounded operators, right? These operators are bounded, and you have sigma b, right? You just take the resolvent, take a point which is not in here, right? Take the resolvent set. So what it means is that by shifting A and B, right? For example, by shifting A, okay, you can say that sigma of A, adding a constant, you can say that sigma of A is just minus norm of A plus norm of A, right? Just by changing A by a constant. Okay? And so you can transform this into a norm bound, right? You can transform this. So you can assume by a shift in energy. Well, actually, in this case, it's even better because for the Laplacian, it's already true, right? We don't need to do any shift the way we normalized it. There's nothing to be done. But by shift in energy, we can assume that sigma of A is equal to minus norm A or is contained in minus norm A plus norm A, right? We can assume that this by shift in energy, just by moving the thing. No, we actually don't need to move anything. We just have, that's true. There's nothing to be done. This is just because it's bounded, yeah. There's nothing to be done. But we need, so this is always true. Let me think. What I want to do is that, yeah, but this is not enough. Let me think now. I need to do something else. Okay, so we always have one has this. I don't need to do anything. This is always true. A, right? But I want to do something else. What do I want to do? Let me check now. I want to do something very simple. The one thing I'm a bit puzzled with, I mean, this is going to work for my example, but this is true. Let me think. Is this true that the sum of the spectrum of the sum is contained in the sum of the spectra? I didn't check this one. Let me see if I can find a simple proof. Because here it's actually simpler. I didn't, I mean, I think this is correct, but I didn't check it. So when I prepared the lectures, so what I'm going to do is this is equal to minus norm of Laplacian. So this is equal norm of Laplacian, right? So we have this. And so if Z does not belong to sigma minus Laplacian plus sigma V omega, right? What do I want to do? Sorry. What I want to do is I want to prove that the resolvent does not belong to, I want to prove the complementary, right, for the resolvents, okay? For the resolvent sets, exactly. So if Z doesn't belong to this, then what do I know? I know that Z minus Laplacian omega, all right, plus V omega minus 1, this exists, bounded, let's say. This is bounded, minus Laplacian. This way it's going to be better. This is bounded, right? And so what I want to show is that if I want to show that, let me think. So what I want to show is that the complementary of so so sorry, I want to, this is not, as I said, minus Laplacian plus V omega. Then there are two things, right? Then either, if this does not belong to this sum, then it means that, what? It means that Z minus spectrum of V omega doesn't belong to, means that for any lambda in the spectrum of V omega, we have that Z minus lambda is larger than what? It's larger than the norm of the Laplacian. Oops, sorry. Right, this is the same thing. Okay, because it doesn't speak, and the spectrum is just minus norm plus norm, so it's larger than norm of a Laplacian. So it means that if I look at if I look now at the following thing, I want to do the following. I just want to find a norm bound. I want to, okay, another way to write it is that, let me think. What is the easiest? What I want to do is Z minus Laplacian minus V omega. I want to show that I can define this, right? And I want to do it as simple as possible. Okay, yeah. So what I do is the following thing. I write this, of course, as Z minus V omega minus 1. So I write this as Z minus V omega minus 1. Okay, 1 minus, and here you have Z minus, sorry, this way, Z minus V omega minus 1 Laplacian, right? And I have a plus maybe here, right, here. Okay, so for Z not belonging to the spectrum of V omega, I have this, right? But now we know that if z is not in here, this operator, right, has norm strictly less than 1. Okay? So this one is invertible, right? Because 0 is inside here, 0 being inside here, z not belong to this set means that z doesn't belong to this set in particular. Right? Because 0 is inside the spectrum of the Laplacian. Okay? So what I show is that if z belongs to this, as z satisfies this, we see that this operator is invertible. Right? This one is, because we know that we don't belong to the spectrum. So this operator is invertible. So we belong to the resolvent set. So z does not belong to the spectrum of minus plus v omega. Right? So this does it in one direction. So, and the other way around, we're going to use really the ergodic. So you see here we didn't use any kind of ergodic structure. Right? This is just simple norm bounds. But now in the other direction, right, the fact that this be less than, that this norm be less than 1 is just consequence of this, right? It's just this. And now, in the other way, in the other direction, well, what we're going to do is the following thing. We're going to, pick lambda in the spectrum of v omega. So let me call this, as I said before, in the almost sure spectrum of v omega, right? So easily one sees that the almost sure spectrum of v omega is exactly what I called the support of omega 0, right? So that's the same thing. Right? It's because, what is this? The matrix here is just, you draw infinite many random variables, right, identically with distribution, the distribution of omega 0 and independently, right? So what you obtain just by the law of large number is that the spectrum is just this support, right? Because it's a closed set. And that's the almost sure spectrum. So if you take lambda in omega 0, right, then, and that's where ergodicity comes in. Then, for any L positive, there exists some n such that if you look at, and for any L positive, there exists some n such that if you look at the omega gamma minus this value lambda, right, for all points in the cube centered at n and of radius at most L, this is going to be less than 1 over L. What does it mean? With positive probability. Right? It means that if you take, just because it's ergodic, right, you have your ergodic random field over Zn, it means that I can fix this thing, right? This is as we know that the probability of omega gamma or omega 0 minus lambda less than 1 over L, this is positive. This probability is positive, right? So the probability that the event that you have, that for all omega gammas, right? So what you do is the following thing. So you take ZD. We know that if we take here, centered at 0, this in L, side L, all the values here, all omega gammas satisfy this, right? We know that this event has positive probability, omega. Sorry, this is because then this means that the probability that for all gamma less than n, because they're independent, omega gamma minus lambda larger than 1 over L, this probability, this event has positive probability, right? And now what you do is you just do the following thing. You look at your random field all over ZD, and you split ZD into larger cubes, or cubes of this size if you want. You pave it, right, for cubes of this size, you get IID random variables, okay? And using ergodicity, right, you know that this event, which has a positive probability, right, well, you know that just using what is it? Yeah, just ergodicity, it shows you that there exists actually infinitely many of these cubes where this event is going to happen. Right? You're going to have infinitely many cubes in space where this event is going to happen. So at some point, this is going to happen. Right? This is ergodicity. So you have, this has a positive probability. But now, what we know, but we can now take a function, let phi, no, but let E be a point in the spectrum of the Laplacian, right? And then we know that we can find there exists a function phi, so for any delta positive, there exists an L positive and phi function which is supported in a finite cube, and phi belonging to what? To L2 ZD, such that phi of phi of gamma is equal to 0 if gamma is larger than L, right? So it's supported in a finite cube, and minus Laplacian minus E applied to phi in norm is less than delta. This just comes from the exact characterization of the spectrum of the Laplacian, right? It's a Fourier multiplier. So where does this come from? This comes from, this is where you use the fact that the Laplacian is a Fourier multiplier, indeed. What are there are no eigenvalues. Laplacian doesn't have any eigenvalues, right? Its spectrum is purely absolutely continuous, right? So what we know is that the Fourier transformation from L2 ZD to L2 on the torus is RD divided by 2 pi ZD, right? So this is Fourier transform. Well, if you look at the minus Laplacian, so you go from this way, I should take F star. This is equal just to the multiplication. So this is an operator. It's equal to twice the cosine of theta I going from 1 to D, right? Where the theta I run over the torus. Okay? And now what you do is, you just do the following. You do the following. You do take the function, so pick theta I such that the sum, twice the sum cosine theta I zeros, for example, is equal to E, I going from 1 to D, right? Take chi in C0 infinity of the torus, in C infinity of the torus, supported near theta 0, such that what? Such that if I look at 2 sum I equals 1 to D cosine theta I minus E is less than the sup of this, the supremum of this over the support of chi be less than delta over 2. Right? So this function over the support of chi the function cosine is close to the value 0. Or if you want, another way to say it is you just take supported, well, yeah, okay, this is already said supported near theta 0. And so, if you now look at chi hat, which belongs to L2 ZD, what do you know? Well, you know that minus Laplacian minus E chi hat, this, and I take chi normalized, right? I know that this is going to be less than delta over 2, right? Because this is just right, by Fourier transformation, because the Fourier transformation is unitary. Okay, so this is less than delta over 2. And once this is less than delta over 2, what you do is you just, and the other thing you know is that, moreover, because chi is C infinity, moreover, we know that chi hat at n for any k, so this is a function with rapid decay, it's the k is larger than, right, for any k, we know that the Fourier transform, Fourier coefficients, decay faster than any inverse power, right, because it's a C infinity function. And so what we can do is we can just truncate it, right, to choose a k that is summable. So if we set what? If we set chi, so what did I want? I wanted delta over there. If we set chi L, phi L is equal to chi hat times the characteristic function of the gamma less than L, right? Plugging this into here, we have, one has, that minus Laplacian minus E phi L is less than delta over 2 plus the sum over the gamma is larger than L of Ck length of gamma to the minus k. Right? This just comes from, and because in here you have a constant C, right? It just uses the fact that this is a bounded operator. Okay? And we know that phi L in norm is equal to 1, which is the norm, this is L2 norm, 1 plus chi hat plus O of sum, well, I can put, I could put the constant here, Ck, just remove it, sum of gamma to the minus k, gamma larger than L. Right, you have this. And we see that if we take L larger, now take k larger than the dimension, plus 1, so that these sums are converging, right? So the remainder goes to 0. So taking L sufficiently large, this is less than delta over 4, for example, and this is larger than delta over 4, do the division, and you get to just renormalize this vector, right, phi L, so that has norm 1, and you get what you want. Okay? So this proves the existence of this vector, right? And once this is proved, well, we just need to do the following. We can just shift the vector, right? Instead of taking this one, we translate it so as to have center in n. Sure.
Norm of phi is equal to 1.
This one here, yeah, we're going to choose norm of phi, exactly, equal to 1. Right? This is what we achieve by doing this. And now what we do is we just shift it. We just shift it. So now you take, for any L, so you take this, what you have above here, right? And what you get is then for omega, no, sorry, here there is something missing. There is something better than what I said. with actually, this happens with probability 1, right? Because of ergodicity. It happens with positive probability, right? But this event now happens with probability 1 because it's ergodic, right? Because the probability is positive and the event is actually an event in the tail algebra. So you have either it happens with probability 0 or probability 1. So it's probability 1 because it's positive, okay? So with probability 1. So you take an omega in this. And then what you do is just the following thing. You take, let phi n be tau n phi, meaning phi n of gamma is phi of gamma minus n. So you center the vector in n, right? The n being this one. And then if you apply minus Laplacian plus v omega to phi n, right? What you get is that this is equal to, minus e minus lambda phi n. This is going to be less than, well, 1 over L plus delta. Right, the delta down there and the 1 over L. And this we can make as small times phi n, because the norm of course does not change. And this we can make as small as you want, right? You can choose an L arbitrarily large. Sorry, you can choose a delta first, and then you choose the L large enough so that actually this is less than delta as well, right? You can always choose the L large enough. You have it for a small one, take a larger one, it works still. So that this is less than delta. And we get that the distance of E plus lambda to the spectrum of minus Laplacian plus V omega is less than 2 delta. Right? And so this proves that, and this for any delta. So we get, so this is the almost sure, this is the almost sure spectrum, this is sigma. So it's the almost sure spectrum of H omega. Right, this is a fixed set. And well, this is finished now. Okay, it proves that the sum, so this is any value in the spectrum of the Laplacian, and this is any value in the support of omega 0 or the spectrum of V omega. So this proves. Hence, so this is hence sigma minus Laplacian. So you see that here we use the structure of the model, right? It's not just an arbitrary random, arbitrary ergodic operator, right? We really use the fact that we could construct quasimodes, and we used Weil sequences actually. We used Weil sequences to approximate the spectrum. Okay. So how is it? Okay. Okay. So in general, it's not so easy to compute what the spectrum is. For the models I presented last time, it is known in many cases what the spectrum is. But for a general model, it's not that easy to compute, right? I mean, it's natural that it wouldn't be that easy, right? Because it's not very easy to compute what spectrum of a large matrix is. But usually you can extract some simple facts. Right? For example, one model for which it was not known until recently what the spectrum was, or actually it's not known what the spectrum exactly is, but it wasn't even known what the bottom of the spectrum is. It was known that the spectrum is contained in a half-line, right? But one didn't know where the half-line started, right? The infimum of the spectrum was not known, is the displacement model. And actually, it's only recent results from 2009 where people managed to compute it, right? It took some time. So the next thing I'm going to introduce, and this is in the new chapter, is the density of states. It's an important quantity. And it's related to the spectrum measure, but it's just an averaging of the spectrum measure. So what is it? So here now, actually in all the remaining chapters of the course, we're going to restrict ourselves. So we consider random Schrödinger operators on either L2 ZD or L2 RD. Right? I always work in these Hilbert spaces. And the other thing that I'm going to consider, the ergodic transformations will be either the translations T gamma for gamma in ZD or T gamma for gamma in RD. Right? So this is just where T gamma acts from, well, H. So this is H to H, so either a vector or function, such that U is sent to T gamma of U at, let me write it, X, is U at X minus gamma. So it may be a discrete or continuous variable, but it's just the translations, right? This is the models that I have in mind. So it's all the models I gave at the beginning. And I'll mainly actually restrict myself to L2 ZD for the computations I'll do. So let's consider, let's say on L2 ZD, consider H omega equals minus Laplacian plus V omega, right, where V is a potential. V omega U at N is what gamma is omega gamma U gamma. I don't say what omega, these are random variables, but I don't assume them to be, well, yeah, we can assume them to be IID. Let's say, to make things simple. Okay, now, and what I'm going to do is the following thing. So let lambda be a cube in ZD, be a cube, right? Okay, so something of the following thing, intersected with ZD. I will not always write the intersection, right? I keep in mind that I'm in ZD, I just keep the same notation. And I can define two things. Well, I can define two things to define the density of states. Actually, there are many things. I can, so consider H omega restricted to the cube lambda, which I always sometimes write lambda L, right? Restricted to the cube lambda L, what is it? It's just that you do the following. You take H omega and you project on both sides by lambda L, right? Just restrict. So you look at this, meaning that you look at H omega. So what is this? This one lambda L is just a natural projector from L2 ZD to L2 lambda L, which to a vector U associates the vector U gamma. Right, you just keep the coordinates in lambda L. That's all. So if you think of, in dimension 1, if you think of your infinite matrix with ones here, omega gammas here, and ones in the lower diagonal, right? The only thing that you do is you cut off a finite dimensional matrix where you have lambda L here and lambda L here, right? Just take a window, give you a finite dimensional matrix. So here you have a self-adjoint. It's a finite, this is always a finite dimensional matrix, right? Of size lambda L times volume of lambda L times volume of lambda L, right? And you can define, so it's this matrix, you can define nu sub L. So the following measure. So what is it? So nu sub L applied to a function phi. I'm going to define it by duality, applying this measure, computing the integral of the function with respect to this measure, which is just the trace of phi of H omega restricted to lambda L. Right? I just take the trace. So this is a finite dimensional matrix. Okay? And I take the trace, the function of this finite dimensional matrix, well known what it is, right? You can do it for polynomials and then extend it because it's just a bounded operator, that's fine. And well, I'm going to normalize it by the volume as well. Right? That's nu of L. And then I'm going to define another one. Couldn't define many because you see here I took some special boundary conditions, right? By doing this, that's just defining boundary conditions, setting this boundary conditions to be 0 everywhere here, right? But I could use other boundary conditions. There is another way to do this, which I call nu tilde. To be, so this is, for example, for phi continuous functions over the real line that, well, actually continuous. This operator is bounded, right? And its spectrum is contained inside a compact set which is independent of lambda L, right? So I can actually define this on continuous functions. It's nicely defined, right? The spectrum, notice, so if, note that if the random variables are bounded, then the spectrum of H omega lambda L is contained in minus R for any omega and any L, right? There exists some R such that this is contained in the compact set minus RR independently of omega and L. This is just because you see these are bounded. So if you increase the size of matrix, it does not change the size of the norm of the matrix, right? Because norm is just given by the soup of these elements, because they're bounded. And the Laplacian here is a bound operator. So here the only thing when you look at this matrix is nothing but to apply the Laplacian to some vector with a fixed support. So it's certainly, the norm of this matrix is certainly bounded by the norm of the Laplacian on the whole L2ZD. Right? And so you get that. You have this. So you can define this for any continuous function. There's nothing at infinity, right? There's no problem with that. These are bounded operators, uniformly bounded. And here I can define nu tilde in the following way, which is still, so both have their own advantage. Trace of, and I take phi of the whole random operator. And now here I restrict this. So this is an infinite matrix, okay? And I restrict this to the cube lambda L. So here you have an infinite matrix, but I can restrict this infinite matrix in the same sense as here to the cube lambda L. I have a finite matrix, finite dimensional matrix, and then I can take its trace. This is certainly trace class. Right? You can do these two things. So see, here is defining the operator restricted to some finite block with some boundary conditions. Of course, I chose some boundary conditions, but you can choose other ones. Right? I'll give you another result a priori for this matrix. But you can also do it by taking the whole random operator, okay, applying the function to it, so, and then restricting this to some finite cube. And one has the following thing. So it's a theorem definition. One has, okay, theorem, which is also a definition at the same time, it defines an object. There exists a new compactly supported measure on positive measure on R such that omega almost surely when L goes to infinity, well, you have that nu L converges to nu and nu tilde L converges to the same nu, and this converges, this is as L goes to infinity, this convergence is weak or vague, if you want, this is the vague convergence. So what does it mean? It just means that these things converge, right? for any continuous function, we have that nu L phi converges to nu phi, which is also the limit of nu tilde L phi. Okay, so let's prove this. And this nu is called the density of states. Nu is the density of states measure. Of h omega. So one thing one should note is, you see, if you look at this definition at nu L, what is nu L? Another way to define nu L. Remark. Clearly, h omega L, h omega restrict to lambda L, this is a finite dimensional matrix, right? So its spectrum is pure point. So this has eigenvalues, which I call E1 omega until E volume of lambda L of omega, right? And what is nu L? Nu L applied to phi is nothing but 1 over the volume lambda L, the sum for, I just compute what this trace is, for k going from 1 to volume lambda L of phi of ek of omega. Right? That's the only thing that it is. Okay. So what does it mean? It means that nu L is also the integral of phi against what? Against what is called the counting function, dn omega L, right? Where n omega L of E is nothing but the number of eigenvalues of h omega restricted to lambda L less than E divided by the volume of lambda L. Right? This is a counting function, and at every eigenvalue it jumps. When you pass an eigenvalue coming from below going to above the eigenvalue, it jumps up by an amount which is the multiplicity of the eigenvalue divided by the volume of the cube. Right? And here we get this. And so this is where the name density of states comes from, because what it says is that you count the number of eigenvalues below energy E per unit of volume. Right? It counts the number of eigenvalues per unit of volume. So let's prove just these two things. The first one is actually quite easy. Proof, and will give us the value. Oh yeah, I should have written this here. Okay, I'll write it. It's going to be written below. Let's start with nu tilde L. Okay. Nu tilde L applied to phi. Well, what is this? This is 1 over the volume lambda L of the trace of phi h omega times the characteristic function of lambda L, right? But this, of course, is also 1 over the volume lambda L, the sum for gamma in lambda L of trace of, delta gamma. So I just write this as being the sum of, this is the sum of delta gamma tensor delta gamma, where gamma runs in over lambda L. So it's this, phi h omega delta gamma. Right? I just compute this trace inside the basis delta gamma. So delta gamma is just a vector that puts 1 exactly at the side gamma and 0 elsewhere. Right? It's just a standard orthonormal basis for my L2ZD. Okay? And so this is equal to, well, now we use the ergodicity. delta 0 phi h tau gamma omega delta 0, right? We use the fact that this is as h tau gamma omega. So if you shift gamma, you get that this also, I use the same letter, I shouldn't, but I understand. So these are the shifts in L2ZD, right? These are the shifts in L2ZD, and these are the shifts in the probability space. Right? So I use the ergodicity here. But now what do I have? If I look at the random variable, if I look at this random variable, but this, well, is a random variable, right? The only thing one needs to prove is that this is measurable, but we knew that h omega is weakly measurable, so phi is continuous. You can approximate phi, for example, by linear combinations of resolvents, of 1 over z minus e, right? And so this gives you that this is a random variable. Now, this being a random variable, what do we have here? We have nothing but the space average. Okay? So by the Birkhoff ergodic theorem, we know that this converges omega almost surely as L goes to infinity to the expectation of delta phi h omega delta 0, right? It just converges to this. That's a consequence of ergodicity, of the Birkhoff ergodic theorem. Okay, so this gives the first. Now the second. So, and moreover, it gives you also, so we see, remark, one, if the theorem is correct, so if you prove the second part, one has, nu of phi is just the expectation of delta 0, phi h omega delta 0. Right? It's just the expectation of, so for phi continuous. Right? We computed the limit with a closed formula. This formula I think is called Pasteur's formula. In a more general setting actually. It's also related to sigma algebra, C star algebras, right? And it's called Dixmier trace formula in the sigma algebra formalism. So you find it in a number of settings. Okay, so now the other part. So this was for nu tilde, for nu now. For nu L. Here we're going to proceed a little differently. You see roughly what's the philosophy? I should have said a word about the philosophy. What's the philosophy behind this? It's the following. So nu L phi is 1 over lambda L, trace of phi h omega restricted to lambda L, right? The philosophy is independence from the boundary conditions. Roughly, the idea is the following thing, is that these two operators, h omega lambda L, like this, or phi, let's say, phi of h omega lambda restricted to lambda L, or phi of h omega and the restriction outside, they are essentially the same except for the eigenvalues that really get influenced by the boundary, right? But these eigenvalues should be only there in small numbers, right? Only the eigenfunctions living near the boundary should be influenced by the boundary, right? So, and we are going to prove such a thing, right? By using, so we're going to start with a special family of phi's, pick phi of x to be z minus x inverse, right? Where imaginary part of z doesn't vanish. So we take resolvents. And the first thing that we have, lemma, for z, for lambda 1, actually which one is the bigger one in my notes? For lambda 1 contained in lambda 2 such that, and n belonging to lambda 1 and m belonging to lambda 2 minus lambda 1. For z that is not in the spectrum of h restricted to lambda 1, I dropped the omega because the omega doesn't really play a role. Well, let's say h omega, I'll put it. Nor in the spectrum of h omega restricted to lambda 2. Right? We have that z minus h omega restricted to the bigger one inverse. So you take, so this operator exists, and I look at its kernel at the points n and m. Well, then you can have a resolvent formula. This is equal to minus the sum for k belonging to lambda 1, k prime, or maybe I should use more space actually. I'm going to rewrite the formula up there. So I have that z minus h omega restricted to lambda 2 inverse at n m is equal to minus sum over k in lambda 1, k prime in lambda 2, such that they are distinct by at most 1 of z minus h omega restricted to lambda 2 inverse nk z minus h omega restricted to lambda 1 inverse k prime m. So yeah, maybe I should put this one, would be better. The lambda 1 is here because the n is in lambda 1, right? So this one has only non-trivial elements in lambda 1, and this one only in, well, this one lambda 2, lambda 2. Okay. So the proof of this is just the following thing. What you have, let me draw it as a matrix. You have lambda 2, right? So what do we know? We know that the operator is 0 here, except on the diagonals. Here you have the omegas, here you have 1s on the diagonals, right? And you have lambda 2, and here inside you have a lambda 1 and lambda 1. No. And so what you have is that if you write h on lambda 2, you can write it as h lambda 1, direct sum. So I've dropped the omegas. H lambda 2 minus lambda 1, direct sum. The only thing that's missing is what's happening here. You see? At these boundaries. Actually, the picture is not very good because this is a bit too large, but you have only these boundary points, right? on the boundary points of lambda 1. Right? This is what's happening at the edges of lambda 1. So here you have what is sending every point at the boundary of lambda 1, right? Any k here has how many? D plus 1 points inside lambda 2 minus lambda 1, with which it has some non-zero element for the Laplacian. Right? These are the ones on the off diagonal, on the first off diagonals, right? And D plus 1 of them are inside the complementary, and the other ones are inside the set lambda 1. So you see them here. Okay? And now, so you write, so you have this decomposition, right? This is orthogonal, this one, how should I write it? We have this sum. Okay, and so this tells you roughly that, well, it's inside the matrix, but you have, so and now you just invert this, right? You just invert this. Okay, so you have that. So you invert this blockwise, right? You do the block inversion. And what happens is that here, because I took 1 point, this one is in lambda 1 and this one is in lambda 2, the diagonal part does not exist. Right? There is no diagonal part. The only thing that comes from the diagonal is, so what you have is roughly something here. You have this is in lambda 1. Here you have, so if you want, you have here lambda 1, lambda 1. I change the matrix, I renumber. Here you have lambda 2 minus lambda 1. Lambda 1. And here you have some interaction terms, right? Which is given by this. Okay? And so if you do now, if you look at this, it means that you take the inverse of this matrix and look at it where? You look at it in here, in this corner, right? But in this corner, this does not contribute, then this block does not contribute either, except through these mixing terms, right? And when you do the computation, you get this. Okay, I don't want to write it down completely, but it's a simple computation to be done. By the way, if you want to find it, you can find it in the notes in the lecture notes by Kirsch. Actually, you can look at the Kirsch lecture notes. I think Peter Zograf posted on the website. He posted the abstract for the courses, right? And you have all the references in there. So there is a nice set of lecture notes by Werner Kirsch, which is available, I think, from Archive, and there you'll find all of this material written properly. So, and now we're going to use this formula to get the convergence for the other thing. So what we are interested in, what we want to do is the following. Oops. Right. Okay, so we want to estimate now. I want to take h omega minus z, or z minus h omega, sorry. Z minus h omega inverse at, and so I want to apply it for lambda 2 equals zd and lambda 1 equals lambda l. Right? I want to apply this for lambda 2 equals zd and lambda 1 equals lambda l. So I want to look at the trace of this. So I want to estimate this at gamma minus gamma prime minus z minus h omega restricted to lambda l minus 1 at gamma prime. Right? I want to look at this. Well, actually, I can look at this. Just I'd be interested in the diagonal elements, right? I want to estimate the difference of the traces, right? So I just look at the diagonal elements. Right? And I'm interested in this, of course, for gamma in lambda L. Okay. And then So I can use this formula. This is equal, right? Let me think now. Right, exactly. I use gamma lambda L, right? Lambda, this is lambda. This is lambda L, and this is in ZD, so I can take lambda 1 is contained in here. Right, the formula is correct if I work in lambda 1. Okay? So I use gamma and lambda L. So this, by this formula, is just the sum for k in lambda, lambda L, k prime, k minus k prime. So k prime, there's no condition on k prime, so it's just the nearest neighbor. Z minus h omega in lambda L inverse. Here I have, this one is gamma k times z minus h omega in lambda in ZD, and all in all, so it's k prime gamma. Right, that's the only thing. And now, each matrix element here, because imaginary part of Z is positive, you can bound this simply by the following thing. You can bound this by what? Each of these things, this thing can be bounded by 1 over imaginary part of Z. Right? This is because it's just, this operator has norm bounded by 1 imaginary part of Z, and what you do is you take the operator applied to delta gamma, scalar delta k, but these have norm 1. Okay, so you get that this is bounded by this one as well. Okay, so this sum here is bounded by what? It's bounded by twice, or by a constant, the volume of the boundary, because the number of points that you have here, right? For every k, so you sum over the boundary, and then you take all the nearest neighbors in the complementary, right? But this is bounded by a constant times boundary. Constant depends on dimension. Okay, divided by imaginary part of z squared. Right? But here we're interested in not this, but we're interested in divided by the volume, remember? So what you have here, right? What did I do? No. There's oh yeah, sorry. There's some, no. There is something that I'm doing wrong. Sorry, I'm doing, this is too fast. This is correct, but it's not good enough. This is correct, but it's not good enough. Why? Show you why. So here, it won't be good enough. So this is correct, that this is bounded by imaginary part of Z, but this is not what we're going to do. What we're going to do is we're going to use the Cauchy-Schwarz inequality. So this is 1 over lambda. Let's remove it for the moment. I don't need it. We're going to use the Cauchy-Schwarz inequality and say that this is less than the k belonging to, so this is lambda 2, so lambda L. So this, the k's, because they satisfy this, and this k prime, is in the complementary of lambda L. So because they satisfy this, it's bounded by the sum over the k's in the boundary of lambda L, right? Of z minus h omega lambda L inverse gamma k modulus squared, right? I just use Cauchy-Schwarz plus, and I do the same thing here, k prime belonging to the boundary of the complementary of lambda L, z minus h omega inverse k prime gamma squared. Right, this I just used Cauchy-Schwarz here, right? And then I used AB, so I can take a 1/2 here. AB less than 1/2 A squared plus B squared, right? To separate this in this way. But now what do I have here? You see, when gamma is fixed, what is this? Now I want to understand, so how do I write, what is this? This is just, this I can write, for example, as the sum over the k primes Well, now I'm going to do the summing over gamma. Now I want to sum. Now I want to sum this over gamma in lambda L. So it's bounded by the sum of this. Sum of this gamma in lambda L. And I want to divide by 1 over the volume. Okay? But now look, if I do the sum of this over gamma in lambda L, right? How can I rewrite this? I can rewrite that this is nothing but, I look at the vector, so I invert the two sums. So this is sum over, maybe I do it for this one first. This one. I rewrite it as, I do the sum over the k in the boundary of lambda L, 1 over the volume. And here I do that this is the sum over gamma in lambda L of what? Of z minus h omega lambda L inverse gamma k squared. But this is just the norm. That is just the norm squared of the vector z minus h omega lambda L delta k squared. Sorry, inverse here. Right? Because I sum over all these elements. That's the norm of this vector. Right? So this is bounded by 1 over imaginary part of z squared. Right? And this is the way I got rid of this sum. That's important. If I don't get rid of this sum, I'm going to be in trouble in a second. Right? Okay? And here you do the same thing. You do the same bound on this side. Okay? So what do I get? I get that this is bounded by 1 over the volume plus the sum over k in delta lambda L plus the sum over k prime in delta in the complementary, in the boundary of the complementary of lambda L of 1 imaginary part of z squared. Right? But this now, But this now is bounded by a constant times the volume of the boundary. These two boundaries, right, have the same volume up to a constant. Divided by imaginary part of z squared divided by volume of lambda L. This is what I wanted.
Sorry, where is the subtracted term? The resultant of...
Okay, so we wanted to estimate the trace of this. Right? But what I'm saying is now, if I estimate the trace of this minus this, right? So this tells you, so what we proved here is the following. What we have proved here is that if I take, so what we get here is that if I take the trace of z minus h omega inverse times 1 over lambda L, 1 over the volume L minus the trace of z minus h omega restrict to lambda L inverse, right? This difference is bounded by this difference.
Yes, but when we used this formula, we didn't where gone this subtracted term.
But here oh, forgot. Yeah, I forgot the part of the formula. This is why. Let me think now. This, did I write this properly? Let me think. Okay, I see what you mean. I see your problem. What did I? What did I do here? I forgot part of the formula, but what did I do in my notes here? Oh yeah, sure. This is because I take the formula, right? Here I wrote the formula for, this is what I said. I took m in lambda 2 minus lambda 1, right? The part here is that, yeah, sorry, this formula, I copied these notes, but there was this is what I said before, is that if you take it, right, if you take it in z minus h omega lambda 2 inverse n m. So if you take n and m in lambda 1 squared, so here I have it for lambda 2 minus 1, 1, minus z minus h omega lambda 1 n m, well, you get the same result. Right? This is because of this, oops, where is the square matrix? Here it is. Okay, lambda 1. Okay, I take the big one here. I take an element, so I take this inverse. I take an element here, right? I say that the big one minus the smaller one, the inverse of the smaller one, is given by the remainder term that I have here. But I don't understand why I have this on my notes. Let me check. And that's correct. So this is, yeah, exactly. That's correct. This is because I did it. What I wrote is correct. It's this one, but it's not the one I need. The one I need is for n m inside lambda 1, right? Because I take both of here. I take both of them to be inside the smaller cube. I take both of them to be inside the smaller cube, right? So this is correct, but I need to take both of them to be inside the smaller cube, right? And indeed, so you have this term, right? This is if you take. So this was correct, but if you have this formula for the same reason. Okay, it's just as I wrote, h on lambda 2 is h on lambda 2 minus lambda 1 plus direct sum h on lambda 1 plus the gamma lambda 1 lambda 2, right, which is this. So gamma lambda 1 lambda 2 is here. Okay, and so if you invert, if you take h lambda 2 inverse minus z, this can be written as, so h, so this is just the sum, right? These are in direct sum, but this one is not in direct sum, it's just this off-angle term. Lambda 2 minus lambda 1 plus lambda 1 minus z inverse, but this is the same thing as to take this inverse times this inverse, right? It's just to have a matrix which is block diagonal, take inverse, and then you have so I do this, and then I have, so let me think, it's minus, and here I have h lambda 2 minus lambda 1 minus z inverse plus minus 1 gamma lambda 1 lambda 2, and you have h lambda 2 minus z inverse, right? And I think the minus sign is correct. Let me check. This I got on my notes. Yep. Minus sign here is correct. And you see that if you take the two elements to be in lambda 1, then of course it means that you're looking at this part of the matrix, so this drops out. This drops out, right? And you get exactly what is announced, this term plus the remainder that's up there. Right? But you're right, it's not what I used is not this formula. I use the formula when you are both inside the small block here. Okay, so we have this. So this is bounded by c times and so we know already that this one converges, right? So this converges as L goes to infinity, omega almost surely to nu applied to z minus lambda inverse, and so we get convergence for that side. Okay. Okay, and once you have it for this, you use just the density, right, the Stone-Weierstrass theorem, density of all the linear combinations of this inside the continuous functions, right? And the second thing you can see is that from there, you can see that the measure actually is positive. The measure d nu, note that we have the closed formula. Nu applied to phi is integral of, it's the expectation of delta 0 phi of h omega delta 0, right? And it is positive if phi is positive. Right? It's positive if phi is positive, obviously from this formula. Right? Phi is positive, this is a positive operator, so if you take this scalar product, it's positive. Take the expectation, it stays positive. And what does this tell you? It tells you the following thing. It tells you that nu is a positive measure. Right? And using this positivity, you can actually prove, it's standard in the following corollary, which is the following, what do I want? If I look at nu L of from minus infinity to E, right? Omega almost surely for E real, this converges to nu, and it's also the limit of nu tilde L minus infinity to E. Meaning that instead of looking at continuous function here, you take the characteristic function of the interval, you still get the same convergence, right? And that's the result of the positivity of the measure. I mean, it's just the fact that you squeeze, right, the characteristic function between two functions like this, right, and use positivity to show that you have upper and lower bounds, get the convergence, right, on both sides, and then you end up by limiting argument. Okay, but actually you can show using this that you have convergence for any bounded measurable function. Okay, and the two things that you get, theorem. If you look at the support of nu, this is equal to the almost sure spectrum. And this is still for the Anderson model. If you look at the density of states applied to a given point, this is 0. So nu, the measure nu is continuous. It has no Dirac mass. These 2 points actually so this one is true quite generally, but this one really relies, proof, the point 2, 1 and 2, really relies on the discrete spectrum. So 1 is actually quite easy. Look, just look at the formula. Nu of phi is delta 0 phi h omega delta 0. So if you take a phi which is supported outside the almost sure spectrum, this is 0 for almost every omega. So the integral is 0, right? So it gives you immediately that, so this formula implies immediately that the support of nu is contained in sigma. Right? If you take anything phi supported outside sigma, then phi of h omega is almost surely 0. Okay? And so this integral, this expectation is also almost surely 0. This expectation is 0, sorry, not almost surely, it's an expectation, it's 0. Okay? And now the other way around. Well, we're going to use, the construction is about the same as As before, what you have is that, let me think now. So what do I do for the other way? Do I need to do something? So I have this now. Yeah, okay, this is use the positivity. Now I assume that this expectation is 0, right? Assume that this expectation is 0. Then actually what you have is that what you can do is the following thing. You can write this also as 1 over lambda L. It's the same thing, these are equal, right? Delta gamma L gamma. So this is also right. You can write this in this way. And so assume that nu of phi is 0. Okay? So it means that these numbers are almost surely 0, but that's the sum of positive numbers, right? So it means that actually this equals 0 means that omega almost surely you have delta gamma phi h omega delta gamma is 0, right? And so what you want to draw is that from knowing this pointwise, you want to know that phi of h omega is 0, right? Because if you know that phi of h omega is 0, it means that phi is supported outside of the spectrum, right? So that's the only thing you need to understand. Okay. Let me think. Okay, yeah, and if you know that all of these are 0, by polarization, right? By polarization, you know that delta gamma phi h omega delta beta, they are equal to 0. Just using this can be written as, oh no, you have to do something. Yeah, what you do is you do it here, you take delta gamma, you change the basis. You need something more actually. You need something more because what you do is you change the basis, right? Once you have this, it means that for any basis in lambda L, you have the same result because this is a trace of a restriction, right? But then what you do is you change a basis so that you also have it for the vector delta gamma plus delta beta. This one is inside the basis. And delta gamma minus delta beta, and delta gamma plus I delta beta, and delta gamma minus I delta beta, you take all these vectors inside the basis, right? Basis for each vector. So then you can use polarization. And you get this equals 0 for all gamma beta. But once you have this equal to 0 for all gamma beta, what you get is that this operator has to be 0 because all its matrix elements are 0. Right? This only shows the zeros on the diagonal. Right? This shows that the matrix elements of this operator are 0 on the diagonal. But if you get it for all gamma beta, the matrix elements of this operator are all 0, so the operator has to be 0. It is 0. And so this gives you the fact that you have the other inclusion. Now, the other thing here, this one now, the 2, so this gives you 1. And the 2, well, comes from the fact it's only okay in the discrete. Uses discrete operators. And it uses actually more than discrete operators. It uses really the fact that the Laplacian, it uses the fact that Laplacian has finite range. Uses Laplacian as finite range. So what's the idea? It's very simple. It's just what is the multiplicity of an eigenvalue for the discrete Laplacian. Okay, so take omega, h omega restricted to lambda L, right? And let E belong to the spectrum of this. Let E belong to the spectrum of h omega lambda L. So one has the following thing. The rank of the kernel of h omega restricted to lambda L minus E, well, this is bounded from above by the a constant times the volume of the boundary of lambda L. Right? It's just because a total picture. I have lambda L here. Right? Here I know that the eigenfunction is 0. Right? It's 0 all over the boundary. If I fix the values of a given eigenfunction on these points here, then just by the equation, I can reconstruct the value all inside the remaining part of the cube. So what does it mean? It means that this linear space is actually spanned, right, by vectors that are determined by just the values here. So its dimension is bounded by the dimension of the boundary set, the interior boundary set. Right? This is because the Laplacian is nearest neighbor. Right? So you know that you have this bound. But then it means that if I look at the trace of of the characteristic function 1 over e h omega restrict to lambda L divided by 1 over lambda L, we know that this converges, this on the one hand converges to nu at the point E, and on the other hand converges to what? To 0. Right? This is why do we have this? This again is by the extension, right? It's once you have this, you use the increasing thing to show that you also have it pointwise. The nu L converges pointwise for a given E. Nu L of E converges to nu at the point E. Right? And here it converges by 0 to 0 because you divide by the volume. So what you get is that the density of states, this gives you that if you look at, so in the discrete case, if you look at the function, right, this function, of course it's increasing. At minus infinity, it tends to 0. At plus infinity, it tends to 1. And it is continuous. Right? Because it doesn't put any mass on a given point. And now there is a famous conjecture, which is open for 50 years, that this stays true, right, for any ergodic operator on RD or ZD. Conjecture. So you can define the density of states. I defined it in this in the discrete case, but you can define conjecture. If, for example, one way to conjecture it, if one replaces Laplacian, right, minus Laplacian by h h0, where this is still, I still take it as a Fourier multiplier, where h0 has the symbol, what is it? h0 of k. Let me write it. What does it mean? It means that has the symbol h0 of k, where, so what do I take? I take h0 is a matrix, so it's the matrix h0, h0 hat of theta. Yeah, take it h0 hat. Yeah. So it's h of k, k prime, right? So it's, I don't do the Fourier multiply, so it's hk minus k prime, so it's the infinite matrix, k, k prime in ZD. Right, I take this infinite matrix. If I take this, and I just assume, well, I don't know, I just assume that sum over, to make sense, I just assume that this is finite. Right, just take this. And then I can do exactly the same things I did. Right, I can define the things exactly in the same way. So this gives you, again, the operator here is bounded. Right? Because this function, this is just sum over hk e to the I pi, not pi, there's k theta, k belonging to ZD, right? So this is a nice bounded function, continuous. And the conjecture is, if one, then the density of states, or the integrated, sorry, this is, yeah, sorry, this thing should have said something. This thing is called the integrated density of states for an obvious reason. Then the integrated density of states is continuous of H0 plus V omega. V omega is still the same thing. It's continuous. To my knowledge, this is not proved, right? And it's quite simple. I mean, it's a very basic fact, but because you lose the argument of the dimension, right? Because as soon as, of course, if this is a trigonometric polynomial, then you can make the same argument work, right? It has finite range. But if it's not a trigonometric polynomial, it's over, right? And of course, more generally, the question is, the conjecture is that a random Schrödinger operator, an ergodic random Schrödinger operator on L2RD has a continuous then integrated density of states. It's defined in the same way, right? You just, I didn't say what the definition of the IDS is in this case, but you can do it in the following way. Where what you do is the following. Take H omega, for example, on RD. Take H omega restrict to lambda L with Dirichlet boundary conditions, right? And you do N L omega of E is the number of eigenvalues of H omega restrict to lambda L with Dirichlet boundary conditions less than E divided by the volume of lambda L, right? And you can show under ergodicity conditions that this converges to N of E omega almost surely. This is the IDS. And so that's the function one has to prove that it's continuous, right? And so under suitable assumptions, we're going to come back to this. Under suitable assumptions on the omegas, right, for the models that we had, for example, the Anderson model and so on, one can prove actually more than continuity, right? But if you take a general model and don't assume anything on the omegas, it's not even known that it's simply continuous. Okay, sorry, as usual, I'm over time. Is this correct, actually? Oh yeah, I'm actually really over time. Should stop me before that, actually, but okay. So we'll see some. Next time I'll give more. I give two important things. First thing is a Wegener estimate that some of you may know, right? And the second thing is Lifshitz tails, right? So we do this next time, and then we go over to localization. Once we have this, in the last two lectures, so next Friday and last two lectures before the holidays, we'll do localization, and afterwards I'll go to the spectral statistics.